last time we introduced the curvature of the measure c square mu, which is defined by the triple integral of 1 over r square x y z d mu x d mu y d mu z, where x, y, z are, is any triple of points in C. X, y, z is any triple points in the complex plane. And R, capital R, so if you have x, y, z, then capital R is just the radius of the circle passing through these 3 points. If all points are situated on the same line, then capital R is infinity. And we considered the connection between L2 norm. Actually, we proved that if we consider C mu epsilon square, the norm of the truncated Cauchy transform, then it's closely it's actually less or equal than curvature of a measure times or of mu. Mu of C. Due to the remarkable identity of Melnikov, I will not write it again. This notion, and we saw how to use this notion to prove the boundedness of Cauchy operator. This notion is very convenient because not only this, because it's geometrical and it's positive, and because it's positive, it's well, it's not easy, but it's possible to estimate this curvature. We will do that later in more general setting. Now, this curvature is well, why curvature? It reflects some geometric properties of the support of a measure. For example, due to David and Leger, Guy David and Leger, 1999, they proved that the following, that let E be a compact, so and finite length, then if we consider the curvature of just one-dimensional Hausdorff measure restricted to E, and if this curvature is finite, then E is rectifiable. So, well, conversely, we will see slightly later, actually, more general statement. So it reflects the some geometry of the set.
Sorry, what's about inverse implication?
Yeah, well, later on we will see even more general statement actually. So we will see that as a corollary of other results, that if compact set is situated on the rectifiable curve and length is positive and finite, then for any for any measure supported on this set with linear growth, the curvature will be finite, actually. So, Melnikov and Tolsa actually gave the solution of the Penlever problem in terms of capacity. They actually proved that for any compact set, not necessarily on the rectifiable curve, for any compact set, the analytic capacity is comparable. Comparable means that ratio is between two constants. It's comparable with the supremum over all, well, I will write sigma 1. And what is sigma 1? Sigma 1 is the class of measures such that measures with linear growth, that is BR is less or equal R. And later, and measures supported on E, of course. And, well, maybe I will write it immediately. What is sigma S? Sigma S is just this class of measures with the growth. So, supremum over all such measures of the following value. Here we have mu of E in 3/2. Here we have curvature plus mu of E in 1/2. So for any compact set, for any compact E in C. That means
I'm sorry, what happens in brackets?
Thank you. In fact, initially Melnikov proved one-side estimate for gamma plus. Actually, he proved estimate for gamma plus from below, and then Tolsa in his dissertation of 1998 proved another side. Well, initially for gamma plus, then for gamma. So it's not just one theorem. This is corollary of several results. What does it mean about removability? That means that E is removable for bounded analytic functions if and only if there is a measure mu of linear growth supported on E. And of course non-zero measure mu of C is positive. So if we find a measure which is supported on E and supported on E, and what is important, with finite curvature, So linear growth and finite curvature, the existence of such measure imply that is not removable. In other words, capacity of E is positive if and only if such measure exists.
The measure assumed to be positive.
Yes. All measures here are positive. Right. usual Borel measure. Is it the answer? Well, in certain term, it's the answer. It's necessary and sufficient condition. Is it geometrical? Is it geometrical description of removable sets? I would say no. Well, what can we say about geometry of removable sets? First of all, we can easily say, we can easily have the answer in terms of dimension, of Hausdorff dimension. In fact, if Hausdorff dimension of E is less than 1, well, in this case, we immediately see that the Hausdorff measure of E is, of course, 0, right? And by Penn-Leviat theorem, we know that the analytic capacity is 0. If dimension, Hausdorff dimension of E is positive, is greater than 1, then actually it's a standard fact in potential theory. There exists measure such that measure supported on E, and such that just the Newtonian potential G mu of xi over xi minus z is bounded. Actually, that means actually that the Newtonian capacity is positive. That is the Newtonian capacity is positive. Well, Newtonian capacity is positive. We conclude that analytic capacity is positive. So gamma of E is positive. So in terms of dimension, we know all cases except dimension 1. So only the sets of dimension 1 are, some of them are removable, some of them are not removable. Well, this is very rough description, of course. Now, to consider more delicate characteristic, we have two definitions. Well, compact set E is said to be purely unrectifiable if one-dimensional Hausdorff measure of intersection E and any rectifiable curve is 0. So for any rectifiable curve. This is one definition. This is purely unrectifiable sets. And at this definition 1 and definition 2, what's the Favart length? So we consider some. So we have some compact set E, and we have some theta, and the straight line, and we consider the projection of the compact set onto this line. We will consider this. We will denote this projection by P theta of E, and we consider the length of this projection. And then we integrate over all theta from 0 to pi. Actually, amazingly, it's the same notion that appeared 2 days ago in the first lecture of Nikolai Kapitonovich. It's I don't know. I told him that. And he said, well, maybe it's some relationship, because he said that every time such coincidences are not incidental. That's what he said. Тут случайностей не бывает. So, and this integral is said to be, maybe we can normalize it if you want. And this is the Favart length of E. Favart length of E. The other name is the Buffon needle probability, because such notion appear in some problem when we put needle incidentally. So, there is it's known, and unfortunately I don't know when it was. Excuse me. Yes. Also, I can write length or h1 of this. It's the same. Okay, it's fine. Well, now, in fact, for sets of finite length, there's the null sets of these two notions are the same. So that means that E is purely unrectifiable if and only if the Favart length is 0. Maybe I will give an example. The standard example in this case is the 1/4 counter set that we met already before. So this is 1/4 and 1/4, and if we consider, for example, if we consider this such a straight line and consider the projection, then one can easily see that the projection will be exactly all line. So the projection will be all line. But there is so in fact, sometimes it's not 0. Well, but the number of such lines is finite for this set. So, and for almost every direction, the length of the projection is 0. It's not a difficult exercise actually. So the Favart length. So the one.
You said it's finite, not countable, but just finite.
I think finite. Yes, I think finite. Well, I said that the number of curves when the projection is all interval, the number of such directions is finite. If you turn it a little bit, the projection will not be all interval. So, 1/4 counter set is an important example of purely unrectifiable set. So I would say that this is maybe the best possible test for that, because how to prove that for any rectifiable curve the length of the intersection will be 0. Okay, now Vitushkin conjecture.
For this set, Favart length is not 0.
For this set, Favart length is 0. And I say that for almost any direction, the length of projection is 0. So for this set, the Favart length is 0. In spite of there are some directions when the length of projection is positive. At the same time, for almost any direction, the length of projection is 0. And the Favart length is 0 for this set. And actually, well, Vitushkin conjectured the following. For any compact set, Favart length analytic capacity is 0. In other words, the set is removable for bounded analytic functions if and only if the Favart length is 0. Well, so in the end of 90th, I think it's 1991, I'm not sure, David proved the following. Let the length of E is finite. Then it's correct. Of course, it's a remarkable result, and the immediate consequence is that for 1/4 contour set, analytic capacity is 0. So this is example of a removable set with positive length, with positive Hausdorff measure. But it turns out that the condition that the length is finite is very essential. In fact, it turns out that it's not correct in general. So there is an example. In fact, that the statement is incorrect was proved by Mattila. And I don't know who found the compact. There exists a compact with 0 Favart length and positive capacity, positive analytic capacity. And so that means that 0 Favart length does not imply 0 capacity. But it's unknown. Is it correct that is it correct? This is a great question. That implies that Favart length. Is it possible to say that analytic capacities is 0, hence so in other words, can we find the compact set E with positive analytic capacity and 0 finite length? Of course, if such compact set exists, it should be with infinite Hausdorff measure, but it's an open question. Well, in fact, the curvature of a measure was important tool to get these results. And this notion actually, shows, well, the same, of course, it holds for gamma plus of E. And using this relation, one can prove the semi-additivity of analytic capacity, actually. So it's very important in many implications. So, I think this is, at least for sets with finite length, this is the quite natural description of removable sets. They are removable if and only if the forward length is 0. Well, and to conclude this part concerning analytic capacity, before we will consider generalizations, I would like to remark the following. When we consider removable singularities, we just, it's important only if analytic capacity is 0 or it's not 0. So, in fact, the value of analytic capacity itself is not important. The first who showed the importance of the value of analytic capacity was Vitushkin. Actually, he used analytic capacity and its counterpart, so-called continuous analytic capacity, continuous C of E. Continuous analytic capacity well, we can introduce it in the same way as supremum of derivatives at infinity, where supremum is taken not only over the functions bounded by 1, but in additional property that f is continuous in C. Of course, C of E is less or equal than gamma of E, but and it's very easy to find an example when really one of them, well, analytic capacity is positive and continuous capacity is 0. Actually, they are not comparable. So both these capacities play very important role in the problems of rational approximation in the complex plane. Actually, this is the main results of Vitushkin and why he was interested in analytic capacity. In this case, in these problems, I repeat, it's important not only to know if it's 0 or not 0, but also the value of capacity itself is important. We will not consider such implication, but it's very interesting. I repeat that. Well, now we saw that our machinery, I mean T1 theorem and our lemma and other two is actually work not only in the complex plane, but actually in metric spaces. So it's natural to consider certain generalization of this notion of analytic capacity. Maybe the first analog of analytic capacity in RG was considered by Paramonov in 1992 when he considered the problem to describe removable singularities for Lipschitz harmonic functions. So, first of all, let us introduce the admissible set of functions. You will see why it's E1. So there's a set of functions. This is functions, set of functions u, which are Lipschitz, locally Lipschitz. In Rg with Lipschitz constant 1, and such that support of Laplacian is in E. The Laplacian is understood in the sense of distributions. Now, L infinity norm is less or equal to 1, and the gradient of U excuse me. No. I'm sorry. Of course it's the gradient of U is less or equal 1, and the gradient at infinity is 0. This is the set of admissible functions, and the Lipschitz harmonic capacity kappa of E is defined by the following. This is the supremum of du1. So this is just the result of the action of this distribution onto the unit function when f is in this class e to L1. Paramonov proved that kappa of E is 0 if and only if E is removable for Lipschitz harmonic functions. For Lipschitz harmonic functions. In fact, if we consider the plane case d equals 2, actually it's easy to see that if gamma E equals to 0, gamma E is, so if E is removable for bounded analytic functions, then it's removable for Lipschitz harmonic functions. Because we know that if we consider harmonic function and consider the partial derivative with respect to z, then we will get the analytic function, right? So u harmonic, then u partial derivative with respect to z is analytic. If in addition we assume that u is in this class, then we will see that our function is bounded analytic, and even bounded by by 2, for example. So this is in H infinity of depends outside of E. So it's clear that if E is removable for H infinity, then it's removable for uz, and it's removable for u, right? In fact, Paramonov proved that for this plane case is less than 2 pi analytic capacity of E. But the inverse statement was open, and at that time it was even not known. Is it correct that any set with even it was known that null sets are the same, that if kappa is 0, then gamma is 0. It was proved later. Actually, it was proved by Guy David. He proved that for sets of finite length, actually, the Lipschitz harmonic capacity is 0 if and only if Favart length is 0. Well, so this is first example of such of related capacities for d greater than 1. Wahlberg considered another version of this capacity, actually. Kappa plus capacity, it's, well, it's the same definition with additional assumption that the distribution is a measure. So the same, well, the same plus distribution du is a measure. Gamma plus of E actually is a direct analog of kappa plus of E is a direct analog of gamma plus of E. Maybe I should remind what does it mean. Gamma plus is the supremum which is taken over all measures supported. So mu of C, supremum taken over all measures supported on C, supported on E, and such that the Cauchy transform of this measure C mu is bounded. Mm-hmm.
So maybe some stupid question, but when we define this
Kappa.
this quantity, yeah, on distribution, we make so why we not use the fact that Laplace is self-adjoint and Laplace of 1 is equal to 0. So looks like if we если мы перекинем Laplace,
There is some boundary values, yes?
Определение распределения, там нет ничего. Там определение для Лапласа распределения, что такое, это просто ликвидируется и все.
Но если ты пишешь формулу интеграла, у тебя должен быть
с
какой-то границ.
компактным носителем.
Ну и что?
Ну и что? Все равно на границе. Ну, знаете,
На границе 0 просто.
Да
Нет,
не 0.
там мера-то и будет сидеть, там она и будет сидеть, это самая мера, вообще-то говоря. Вот на самом деле, если брать вот эти равновесные распределения, там всегда мера будет сидеть на границе. И здесь, в общем, ситуация в чем-то похожая. Нет, там не получится. Ну, внутри, да, а вообще нет, всюду нет.
Другое дело, что вот единица не основная функция, и ее так не подставишь.
В общем, вот если на c0 бесконечность, то вроде...
Нет, ну вот...
Нет, у нас это функции на Е все сингулярные сейчас.
Не, ну вот если это есть мера, то это в точности, получится мера, общая, полная мера. Так что нет, тут все. Well.
Ну, прошу прощения, возьми в качестве У фундаментальное решение.
Ну, я говорю, вопрос может быть глупый. В общем, я спросил,
Нет, он не глупый. Почему? Он совершенно не глупый.
Мне показалось, что там что-то не хватает.
Нет, тут все нормально. Нет, ну вопрос совершенно правильный. I don't know, should I speak what language I should. Okay. So now well, actually, this kappa has very similar properties as analytic capacity. For example, if our compact set E is the subset of Lipschitz graph, then this is just comparable with Hausdorff measure D minus 1 of E.
May I ask one more question? What do you mean by similar in higher dimensions?
By
Similar instead of Cauchy transform in higher dimensions, what do you use instead?
here, well,
Definition of gamma plus.
no, here we consider. No. This is only for d equals 2. This is only for d equals 2. Well, but for high dimensions, this is exactly what I am going to tell about high dimensions and about analogs. This is exactly our next.
I'm sorry, I have a question. What's mean Lipschitz graph for d bigger than 2?
Lipschitz graph.
Yes, cup of E is comparable to this one, yes?
Да, если E лежит на графике Липшицевой поверхности.
Поверхность. А граф Липшицев это вот такое. Ну ладно.
Ну если.
Ладно.
Well, in fact, Wolberg proved that we have that in fact gamma is comparable with gamma plus, and moreover, Wolberg considered the family of capacities that many dimensional capacities that what we consider now. So let us consider Riesz potential of measure mu of x, that is x y minus x to s plus 1. So I should say that we have Rd, I will define d mu of y, where x, y are in Rd, and s is fixed number between 0 and d. Of course, it's the same question how to understand it on the support of the measure. And again, we can say the same as we said when we consider the general Calderon-Zygmund operators. And also, it's a very usual situation when we consider the truncated Riesz potential. This is the vector Riesz potential, of course. And in fact, this Riesz potential can be viewed mu epsilon or just mu, okay, in any sense. It's just 1 minus s of the gradient of usual Riesz potential d mu y, y minus x s minus 1, sorry, s minus 1. Of course, if s is not 1, if s is 1, then gradient of logarithmic potential. And this connection gives us plenty of applications, actually, and shows how it would appear, maybe. Now, as gamma s plus capacity, we understand the supremum of mu of E, where supremum is taken over all measures supported on E, and such that our Riesz transform is bounded by 1 in L infinity norm with respect to the Lebesgue measure. Because S is less than D, this potential converges almost everywhere with respect to the Lebesgue measure, so no problems to define this capacity. In fact, this condition implies the growth. It implies, so this condition implies that measure of the ball is less or equal some constant times r to s. So we can add, and C depends only on D, and D and S. So we can, on G and S, yes. So we can just add additional assumption on the growth, and we will get actually the same capacity, essentially the same capacity. Also, let us consider the Riesz operator R mu epsilon. I will use calligraphic R. F of x is, well, this is the similar definition. Y minus x s plus 1 f of y d mu of y. And of course, no problem to define the L2 norm of this truncated operator. So, and we denote by R mu, the supremum taken over all positive epsilon of L2 norms of this truncated operator. Mu epsilon L2 mu to L2 mu. And if these norms are uniformly bounded, then we will say that this operator is bounded. Actually, it's the direct analog what we considered before. And besides the capacity gamma s plus, we consider so-called operator capacity, gamma operator of E is the supremum of mu of E such that sub mu is in E, of course, and the same is in E. Now we have to add the condition on the growth, mu b. So I would say just mu is in epsilon s, sigma s. We defined this class, right? The class of measures with the growth condition. And such that the norm of the operator is bounded by 1. The operator norm. Well, so gamma s plus, this capacity relates to many capacities we considered before. For example, if we consider d is 2 and s equals 1, then you see that this is exactly the definition of actually of gamma plus capacity. And we saw that gamma plus capacity is comparable with analytic capacity. If d is greater than 2 and s equals d minus 1, then gamma s plus. So in this case, you see that we have actually in this case we will have just a harmonic function, and we will have gradient of harmonic function that is exactly as in the definition of Lipschitz harmonic capacity. So it's comparable with kappa plus Lipschitz harmonic capacity. Actually, for some other parameters, for some other s, it's comparable even with some capacities that appear in nonlinear potential theory, but we will not be able to consider such capacities. Yesterday, we saw already how important is the boundedness of the Cauchy operator, boundedness from L2 to L2, for investigation of the corresponding capacity. Maybe the next theorem gives maybe the most direct connection between these two notions. In the form I formulated, it was proved by Wolberg in 2003, and the theorem is the following. In fact, these two capacities are comparable. So, theorem gamma s plus capacity is so operational capacity is comparable with gamma s plus. So we will sketch the proof of this theorem. In fact, you will see that the methods that were described for solution of Danjoy conjecture work in this case as well. So we will sketch the proof of this theorem, and then we consider certain implications. And in particular, we will get the connection between Hausdorff content and analytic capacity. Well, so sketch of the proof. First step, let us prove that operational capacity is less or equal than some constant gamma. Well, such capacities are called sometimes Calderon-Zygmund capacities. Well, So we take a measure participating in the proof, in the definition of this capacity. So take a measure supported on E with the corresponding growth, and such that operator is bounded. That means that all truncated operators are uniformly bounded. Okay? So all truncated operators, mu epsilon, are uniformly bounding. Uniformly in epsilon. Okay, now, because this is the same problem as last time, of course, for boundedness, we would like to deduce the weak 1-1 type, the weak boundedness. But the corresponding analog of Calderon-Zygmund theorem works only for operators with that map our function, that map measure to continuous function. So again, as before, we consider the modified operator R, okay, R tilde mu epsilon. Actually, this is so we consider y minus x s plus 1, and now phi y minus x over epsilon f of y dy. What does it mean? Phi, it's as before. This is function defined, C infinity function on Rg, and such that something like that. So it's 0 in some neighborhood. This is phi in some neighborhood. For example, it's 0 in one half, and it's 1 here. Actually, we can consider even real valued function. In this case, just put absolute value here. So in this, maybe it's even easier. And in this case, one can easily prove that this is Calderon-Zygmund kernel. At the moment, it's important it's a continuous function. So it sends measures to continuous functions, and we may apply the duality arguments given yesterday. And by we have to prove that these operators are bounded in L2 mu to apply this theorem. Why they are bounded? Because these operators are bounded, and if we consider the difference of these operators, the difference so between the initial truncator operator and modified operator, this difference is dominated by constant times maximal Hardy-Littlewood operator. Well, actually, maybe better to write something like modified. Modification here means that instead of division of mu of b of x r, we divide by mu of x free r. well, if measure is doubling, it does not matter. But here we consider the general setting without doubling condition. And the boundedness of such modified maximal Hardy-Littlewood operator, well, so it is usual g mu of y, was proved by Nazarov, Treil, and Wolberg. So, by our assumption, we see that these operators are bounded. Now, maximal operator is bounded, and we deduce from here that the modified operator is bounded, are bounded uniformly in epsilon. So, using the duality that we considered yesterday, we deduce that there is a function h between 0 and 1 such that integral h g mu is greater than 1/2 mu of e, and such that the operators mu h g mu epsilon are uniformly bounded at any x, right? Now, and here h, of course, depends on epsilon. So we have this family of such functions. Then we take the weak limit of these functions, weak limit of some sequence, and we have function h, and for this function h, we have the bounded operator, the bounded R h g mu is bounded in C infinity, in infinity norm, and we deduce. So this measure participates in the definition of gamma S plus, right? Because it's bounded, and this measure is comparable with mu of E, and we get this inequality. So for any measure participated in the definition of operator capacity, we found a measure which is comparable with this one and which participates in the definition of gamma S plus capacity. And now we get the inequality. Well, this is one side inequality. This is the first part, and the second part the inverse inequality that
Is it right that, roughly speaking, we just substitute some function and get the desired estimate? Substitute the function in the operator that is bounded by assumption.
No.
Truncated operators and some.
What do you mean? No, we don't substitute some concrete function. We just.
I mean the function h. So this is not.
Yeah, right. We found function h. Mm-hmm. Yes, we found function h such that. Well, you're right. I should write r here, just rs. That if we consider our Cauchy operator, our Riesz operator with h d mu here, mm-hmm. then it will be bounded. Mm-hmm. Okay. Now, how to prove the inverse inequality? So we have to prove that that S plus capacity is less or equal than constant times operator capacity. Now we take a measure participating in the definition of gamma S plus. So we take a measure, mu such that mu less than C. Now we will need the so useful concept of the maximal Riesz transform. Maximal Riesz transform are mu star S, so-called maximal Riesz transform of X, is by definition the supremum over epsilon greater than 0 R mu epsilon of X. So this is a so-called maximal Riesz transform, and you see the usual Riesz transform is a vector function. The maximal Riesz transform is non-negative function. And in the same way, we can define maximal Riesz operator, just to add f here and here. And there is the following inequality. That maximal Riesz transform is less or equal than the norm L infinity norm plus 1. Excuse me, I should add constant here. C times. Where constant depends only on S and G. Actually, it's not a difficult result. Well, I don't know, one can meet it in the papers by Wichtela, Wolberg, or some generalization in our paper with Adams. I don't think that Wichtela found it. It's also a kind of folklore. I don't know. So this is for all x. X is in Rg. Now so from here we deduce. This is L infinity norm. From here we deduce that maximal Riesz transform is also bounded in Rg, and that means that all truncated from here we see that all truncated transforms are uniformly bounded that means that less than C, uniformly in epsilon. Now, we would like to use the T1 theorem, because you see, if they, for example, if you will use for some epsilon this inequality, then if function is bounded, then it's in BMO. But if function is in BMO, I quoted yesterday the T1 theorem of Nazarov, Tree, and Wahlberg. If function is in BMO, then corresponding operators are bounded. But it's the problem is that these truncated operators are not operators with Calderon-Zygmund kernels. And again, the same trick works. Again, we consider such operator, and the modified operator R tilde and the truncated operator are bounded simultaneously. This operator is of this operator is operator with Calderon-Zygmund kernel. Calderon-Zygmund kernel implies that we can use the T1 theorem, and by T1 theorem we conclude that our operators are bounded. Well, actually we concluded for R tilde bounded uniformly in L2 mu, and again using Hardy-Littlewood maximal function, we conclude that these operators are bounded uniformly in L2 mu. But if they are bounded, that means that the corresponding measure participates in the definition of operator capacity. I raised it, but you know. So definition of, so they are uniformly bounded. That means this norm is bounded, and that means that mu participates in the definition of operator capacity with some constant, of course, with some constant. And that means that we get this inequality. This is the idea of proof, and actually this is almost the proof. Okay, is it clear? So now we have this very, very important fact. Actually, in implicit form, it was used even in the proof of Dangeau conjecture. Now this is explicit form, and now we now the problem is that if you would like to estimate gamma S plus capacity, how to find the norm of corresponding operators. And in fact, maybe the best way I know to estimate the norms is to use the curvature. Well, of course, curvature was introduced only in the plane case, and now we can consider the analog, the direct analog of curvature. So the analog of curvature the analog is very similar, and so again we would like to find L2 norm of our truncated transform. Then again, we write y minus x s plus 1 integrated with respect to y, g mu of y, right? So I will write it this way, g mu of y, and it will be just the truncated and square. The truncated Riesz transform at the point x. Now we have to square that, right? To square that, we just multiply it by y minus x s plus 1, and here is the scalar product or dot product, and integrate with respect to g mu of z, and this is the square at the point x, and what we have to do, we have to integrate with respect to mu of z, right?
Mu of x.
Oh, x, of course, x. Thank you. Of course, we have. We should take care about truncation. So we integrate y minus x is greater than epsilon, y minus x is greater than epsilon, and then we integrate with respect to g mu of x, and no separation between zx, of course. Excuse me. No separation between z and y. Z and y. So, in fact, we should split the set of triples onto two parts. So we have to symmetrize our domain. So we consider the set z minus y greater than epsilon, and the part over remaining set actually has the same estimation. It's estimated by O by some constant times total measure mu of E. Oh, okay, no, mu of Rn, Rg, plus O mu Rg. And again, as in the case of the curvature, this set is symmetric with respect to all permutations. So we have considered all 6 permutations. Actually, it's enough to consider here just 3 permutations. And when we summarize over all these permutations, we will get the direct analog of the curvature. So, using this approach, together with Nazarov and Wolberg, and in 2010, we got the following. Well, here we just use the growth of the measure, just nothing more. Nothing more is used here. We prove the following: general estimate of the norms. That the norm is less or equal than C supremum over all x in the support of mu. And here we have so-called Wolf potential, namely 1 from 0 to infinity. Here we just take the measure. This is just the average density of the ball. Now square that and integrate dr over r. This is so-called Wolf potential. So we will denote it by w w mu of x, Wolf potential. In fact, no restriction on mu here, except the linear growth, not linear, except the growth. I will I will tell about inverse application slightly later. But at the moment, let me derive certain corollaries from this inequality. The first the corollaries are about connection between our gamma S plus capacity and Hausdorff measure. Actually, I consider it the problem in the case of analytic capacity and gamma plus capacity. I consider it that starting from 1998 maybe, but the general relations for gamma S plus capacities were obtained in our joint paper. So what we can say, first of all, this inequality implies immediately the following inequality for capacity. S plus capacity is greater or equal than some constant supremum total. This is total measure 3 halves integral over all RD Wolf potential x g mu of x in minus 1/2. Actually, this is so-called Wolf energy. Well, and from this inequality, we derive the following. Let mu h, well, not mu was, sorry, m was maximal function, I'm sorry, but also we will denote is the Hausdorff content. Is the Hausdorff content. I follow the notation in the book of Carlson, actually, so it's not my notation. Hausdorff content, what does it mean maybe? This is just the infimum of H R J and infimum is taken over all coverings of the set E by balls. No, so it's not, well, in Hausdorff measure, we cover by balls with radii which does not exceed delta, then take the limit as delta tends to 0. Here is just the cover, any coverings. So for compact sets, this notion, Hausdorff content, is finite every time, but it vanishes simultaneously with Hausdorff measure. So we have the following relation. Gamma S plus of E is greater or equal C, Hausdorff content of E times integral from 0 to t2. I will explain what does it mean. H of t. H is the gauge function or measure function. This one. Over t to s square dt over t to minus 1/2, where t2, well, c depends only on d and s, and t2 is defined by the equality. H of t2 is the Hausdorff content of E. So this is some kind of, oh, but it's clear. So this is the inverse of the Hausdorff content. So expression, this is the relation between gamma and mu. And from here, we deduce the following in the case of vanishing capacity. So, corollary. Let the integral h of t over t to s square dt over t converges in some neighborhood of 0. Then positive, well, I can write Hausdorff content or Hausdorff measure. It's the same, h of E implies that gamma s plus capacity is positive. So, and this statement is sharp. If we consider so sharpness for function h, when this integral diverges, so suppose that this integral diverges, and h satisfies some regularity condition, for example, doubling condition, plus regularity condition on h condition. Doubling condition is more than enough on h. Then there is a compact set E such that Hausdorff measure is positive and capacity is 0. So this condition is sharp. Well, and the example of such a set, this is the counter set actually, and counter set, it's a huge amount of papers concerning the capacity of counter sets and norms of operators on counter sets. But maybe I will have a few minutes. But I would like to discuss, to write some formulas for counter sets. But first of all, I would like to explain what is going on when concerning the inverse estimate. In fact, the inverse estimate was obtained here. So here, let me. The inverse estimate was obtained only by Matthew, Pratt, and Verdera. Only for S between 0 and 1. And this is actually well, why such restriction? Such restriction is because when we consider the sum over all permutations of this product, then it's positive for any triple of points. It's positive when S is between 0 and 1, and when it's positive, then we can get the estimate from below as well, because, well, we can separate all this set onto two parts. One part when this sum is big, right, and just drop the other part, and because it's non-negative, and we will get estimate from below. But when S when S equals 1, it will also non-negative. But if S is greater than 1, it's a disaster. In this case, there are plenty of triples when the curvature is negative. And, well, many people tried to do something to estimate the contribution of good triples and contribution of bad triples, and everybody failed, including the great Fedya Nazarov, because actually the contributions, both of them may go to infinity, and the cancellation of them, it's impossible to estimate. So this is why this problem was open, and Guy David told that in the case when S is greater than 1, the curvature is cruelly missed. Как я понимаю? Жестоко потерян. So it was the only recently 2 papers appeared concerning in the case when S and only when S is between D minus 1 and D. And very recently, it was the first result by J. Nazarov and Wahlberg. This is just a preprint. And they actually proved the following, that if we consider estimate for capacity, well, in estimate I wrote it was the potential, well, it was the Wolf potential, that is well, it was Wolf potential. This one. It was this Wolf potential. And in the estimate of analytic capacity, or capacity S plus, we saw that so gamma S plus, well, so in general, we saw that it was something times the Wolf potential integral RD, and Wolf potential is mu B of x r over r to s square dr r, right? And minus 1/2. Now, Nazarov and Wahlberg, they actually proved the inverse estimate, but instead of this potential, they considered the potential, they considered phi, capital phi, of this density, mu of B of Rx over R to X, GRR. Where phi is it's very small actually. Phi of t is e to minus t to minus beta with certain positive beta. So you see this is a very small function. So because here is minus 1/2, of course it's worse than this one, but and also s is between d minus 1 and d. But at the same time, this is the first quantitative result without curvature. Okay.